Hello and welcome to our final project for design and manufacturing at Georgia Tech with Dr. Rashidi. My name is Declan Campbell. My group mates are Ryan Hockstein and Evan Goldstein. Today we're going to talk to you about some selected topics in the manufacturing industry, many of them related to the Industry 4.0, like emerging technologies and just some general manufacturing topics. So the first topic I'm going to talk to you about is customer value and lean production. Lean production is basically the philosophy that uh, identifying, removing, and eliminating waste is kind of like the most important step of the process of maximizing customer value. So Toyota Production System out in Japan was one of the main pioneers of the system, and they basically classified any inefficient resource allocation into three types. The first type was muda, which can be translated to English as waste. It's any non-value adding activity that is not necessary. There's basically two types that are necessary, like a safety inspection, but something that's not necessary, like extraneous features, that is just considered waste. Mura is the root cause of muda. It's basically unevenness or variation. For instance, one step in like a assembly line getting backed up while another has to wait. That's mura. Muri basically occurs once you've kind of removed a lot of the muda and mura. It basically causes like overburdening and like increased stress for your employees and your machines. So this obviously leads to inefficiencies, so you want to avoid that as well. So this system is it's a very organized and effective way of recognizing and eliminating waste, which is kind of like the most important step in the process of lean production. I feel like this diagram with the trucks really kind of showcased each feature of Muda, Mura, and Murray. The interrelatedness of each concept can make it hard to find optimal solutions, like removing Mura and Muda may lead to Muri, overburdening by removing the waste. So those kind of things need to be considered. The next topic is a lights out factory. A lights out factory leverages many of the new like emerging industry 4.0 topics like robotics, 5G, augmented reality, and it uses these technologies to basically limit the amount of human involvement. It's kind of unrealistic these days to have a factory with no human involvement whatsoever, but many firms are achieving a light sparse manufacturing strategy like Philips and Amazon. So it's kind of like a spectrum, but kind of going towards more of the lights out side of the spectrum can have a lot of benefits, like reducing your labor costs and your error rates. Humans tend to have a lot of errors. There's less safety concerns for the humans as well, and it's really easy to like replicate, these kind of lights out factories just because you can kind of bring your equipment, software, and like you don't to new locations, and there's like less training involved for employees. So here's just kind of an example of this: Amazon developing a very sophisticated piece of technology that humans would typically be doing themselves. The next topic is plastics and their applications. So since they're mentioned in like the early 20th century by Belgian scientist Leo Bacchelid, they've really transformed and kind of dominated material use in the manufacturing industry. Demand for plastics really surged after World War II, during like the 1950s and 60s. As you can see on this graph, it almost like exploded, like exponential rise in terms of the amount of produced and demanded. So it continuously replaced and kind of materials that had been used in products before, like dashboards and cars were usually made out of metal, but then they were eventually replaced with plastic. It's easy to see like the benefits and appeal of plastic. It's very versatile, cost-effective, lightweight. There's a lot of different parameters and properties that you can tweak. So it's very like appealing to engineers as well. And it's often used in textile production, packaging, and it's basically the material of choice for 3D printing, just because of how lightweight and easy to work with it is. The main challenges and limitations of it are environmental concerns. The material itself doesn't really have any weaknesses, but it can lead to pollution just because it's not really biodegradable, and climate change because it requires fossil fuels to make.
Hello, I'm Ryan Hockstein, and I'll be talking about the next 4 selected topics. First, the Industrial Internet of Things, or the IIoT. Have you ever heard the phrase, everything that can be automated will be automated? The Industrial Internet of Things, or IIoT, embodies this concept in manufacturing and industry. Unlike the traditional Internet of Things, which focuses on consumer devices like smart home gadgets, The Industrial Internet of Things connects industrial equipment, enabling smarter factories and real-time decision-making. One example is General Electric's Brilliant Factory, which integrates the IIoT to optimize production lines using sensors, analytics, and AI to predict failures before they happen. This reduces downtime and improves efficiency. The benefits of IIoT are very significant. Real-time monitoring, predictive maintenance, and enhanced productivity are all benefits. There are also some challenges with the IIoT. Firstly, one of these is cybersecurity risks. There can be a lot of issues with cybersecurity once you start adding all of these devices to the cloud. There are also high costs associated with interconnecting all these devices, and data integration can give a lot of complexities that manufacturers are going to need to face. Despite these challenges, IIoT is transforming industries, driving them towards a future where automation isn't just the goal, but the standard. Next, I'm going to be talking about augmented reality, or AR, in manufacturing. Tim Cook once said, AR allows individuals to be present in the world, but hopefully allows an improvement on what's happening presently. Most people don't want to lock themselves out from the world. And this is what distinguishes AR from VR. Because AR overlays digital information onto the real world, it enhances tasks without isolating workers. This is very important because isolating workers could pose a significant safety hazard in manufacturing environments. Boeing uses AR in their wiring harness assembly, where AR glasses display step-by-step instructions, improving accuracy and reducing errors. The benefits are very clear. Immersive worker training, faster assembly processes, and real-time equipment diagnostics are all benefits of AR in manufacturing. Yet, AR does face some challenges. These are high costs and integration with existing systems. Going back to Boeing's AR, it has helped reduce task time by over 20%. And Boeing has ordered 20 HoloLens 2 units for 80 technicians, which is a big jump in its AR scale. It's hard to argue with making your job easier if you're a technician, and many technicians are not too skeptical of the AR as they know it will make their job easier. By bridging the physical and digital, AR empowers workers, improving productivity without detaching them from their environment. Next, I will talk about value stream mapping. Value stream mapping is a very powerful tool for visualizing and improving workflows. Its purpose is simple. You identify waste to streamline the processes and deliver more value to the customer. And the way to do this is by creating a value stream map. One example of this is shown on the right of the slide. Here you have the information flows. You also have material flows and a lead time ladder. All of these come together to create the value stream map. By identifying inefficiencies in this map, you can make targeted improvements. The components include the process flow steps, the material and information flow, like I said, and the timelines. For example, imagine a car manufacturer. Before value stream mapping, their assembly line has bottlenecks, idle times, and excessive inventory. After value stream mapping, they can identify those delays that stem from a poorly timed parts delivery system. Adjusting schedule and lead times, they can reduce these waiting times and save costs. So this is the point of value stream mapping. It transforms messy workflows into lean, efficient systems, making it a cornerstone of operational excellence. And value stream mapping can be applied to many areas of life, not just manufacturing. For example, you can apply a value stream map to your life and to your daily schedule to optimize your time and be more efficient. Finally, I will talk about collaborative robots, or cobots. Collaborative robots are revolutionizing automation by safely working alongside humans in shared spaces. This is different than some traditional robots that require isolation. Cobots are equipped with safety features like force sensors that make sure that they do not cause any harm to workers, and this makes them ideal for collaborative tasks. Cobots excel in various applications such as assembly, quality control, and material handling. One particularly exciting use and common use is cobot welding, which is shown on the picture on the bottom of the screen. These cobot welders assist with precision welding tasks. Cobots can handle repetitive welding operations with incredible accuracy, which reduces human fatigue and ensures consistent quality while reducing the dangers to the workers. This makes them invaluable in industries like automotive and aerospace, where precision is critical and metal is a commonly used parts. Cobots offer numerous benefits. They enhance safety, increase efficiency, and are cost effective, especially for small and medium sized businesses. However, challenges like limited payload capacity and reliance on human oversight still exist. For example, universal robots, cobots, are not only used in the automotive assembly, but also in welding applications. By working hand in hand with human welders, they combine the precision of robotics with human adaptability, creating a more efficient and safer production environment.
Generative design is an AI driven method of exploring design possibilities. By inputting specific constraints like size, weight, materials, and performance goals, engineers can use algorithms to generate optimized solutions tailored to their needs. One of its most exciting aspects is its speed and efficiency. Everyone knows how long it takes to design a complex part. Generative design, however, is able to explore thousands of possibilities in a fraction of that time, often producing results that are more capable and optimized than the way that we could achieve them manually. This technology is being applied in industries like aerospace, where it helps create lightweight yet strong components, reducing fuel consumption. In automobile manufacturing, it supports safety by designing structures that absorb impacts efficiently. Architects use generative design to create sustainable, complex structures that minimize material use. It often incorporates bio inspired design, mimicking structures found in nature, such as honeycomb patterns or tree branches, to achieve optimal strength and efficiency. The main capability of generative design is that engineers can put in new constraints and the software updates design instantly. It's also a go to for creating lightweight and optimized structures. This helps manufacturers meet performance goals while lowering costs. However, generative design is not without its challenges. The computational cost of running these simulations can be significant, requiring powerful hardware and software. Additionally, while the AI generates designs, the output often needs refinement by human engineers to ensure that they are manufacturable and meet practical constraints. The Kano model is a framework that helps businesses understand how product features impact customer satisfaction. As seen in the graph on the right, by categorizing features based on their ability to meet or exceed expectations, the Kano model ensures that products align closely with customer needs. This makes it a valuable tool in product development and manufacturing. In product development, the Cato model helps prioritize features that maximize customer satisfaction. For instance, during the design phase of a new product, the model guides decisions on which features to include based on their expected impact. It's also used to analyze customer feedback, identifying areas where improvements will have the greatest effect. The Kano model classifies product features into three categories. Basic needs are essential features that customers expect. Performance features are those where higher performance lead to increased satisfaction. And finally, delighters are unexpected features that surprise and impress users. The Kano model has its limitations. First, gathering and analyzing customer feedback to determine feature categorization is a time intensive process. Additionally, customer preferences evolve over time. What might start as a delighter can quickly become an expected basic need. This means manufacturers must develop, continuously reassess their features. Digital twins are real time virtual representations of a physical system, combining data from sensors, IoT devices, and simulation technologies. They enable manufacturers to visualize, monitor, and optimize systems in ways that were previously impossible, transforming the efficiency and quality of the product process. One of the most impactful uses of digital twins in manufacturing is predictive maintenance. By continuously monitoring machines through its own digital twin, manufacturers can identify potential failures before they occur, avoiding costly downtime. Another major application is process optimization. Digital twins allow engineers to simulate different scenarios and configurations, finding the most efficient way to operate machines and organize workflows. For example, in a factory assembly line, a digital twin can test how changes in speed or sequencing might improve productivity without disrupting actual operations. Real time monitoring and predictive analytics powered by AI and historical data can forecast potential disruptions, enabling proactive adjustments. Digital twins also enable risk free testing. Manufacturers can simulate changes in the virtual environment before implementing them in the real world. But despite their advantages, digital twins do have limitations. The initial setup costs are high, requiring investment in sensors, simulation software, and skilled personnel. Additionally, they depend on robust IoT infrastructure to ensure accurate real time data collection and communication between the physical and virtual systems.